Okay, now that we know what a linear equation is, let's take a look at what it means to be a system of linear equations. Here's a linear equation, and here's another one. Now you'll notice that those are actually the same linear equation, and I've done that on purpose. I want to find a way to distinguish between these two. Notice that each one of these coefficients, a sub I, could be any real number, including 0. So we might have a couple of equations here that have, one that has some terms and not others, and the second one may have some of the terms that the first one does and not some of the others. Anyway, um, the system of linear equations is more than one linear equation with the same variables. And so each one of them has to be a linear equation, has to meet that definition, and the variables have to be the same, but they can otherwise be pretty much the same. So how can I distinguish between these two generic linear equations? And the answer to that question is that I'm going to add something to the subscripts here. I'm going to say that this first linear equation is not just a sub 1, but it's the first a sub 1, and the first a sub 2, and the first a sub 3, and so on. All right, I'll even call this b sub 1. And the second one is going to be the second a sub 1 and the second a sub 2, and so on. So I'm adding an additional little subscript to my coefficients. So each one of these coefficients is going to be in the form a sub ij, where I tells you which equation does it belong to, the first equation, equation number 1, or the second equation, in this case, equation number 2. That's what the I tells. And what the J tells us is which term in the equation, which position are we at in the equation. So for both equation number 1 and equation number 2, this is the first position. This is the first term, term number 1. And this is term number 2. And this is term number 3, and so on. And we can actually have a third or a fourth or a 10th or a 19th equation, a third equation, linear equation in this system would necessarily look something like this. My third equation, first term. My third equation, second term, and so on. My third equation, nth term, I'm going to call this b sub 3. And I can go in this direction for, indefinitely as well. So let's see, what would happen if we skipped a whole bunch of rows and went to, in the same way that we've gone, so that we have n terms in this direction. What if we have, get rid of that arrow. What if we have a generic large number of equations? Well, I don't want to use n again because I've already used n, and I may have a system of equations that has more equations than it does terms, or vice versa, fewer equations than it does terms. So I'm going to use a different letter to represent the fact that I may have n terms in my equation, but I may not have n equations in my system. I could have a different number. So I'm going to use the letter m for that. M equations. So this is my mth equation, my first term. My mth equation, my second term. Oops, forgot that second subscript there. My second term, and so on. So my system of equations has n terms in it. Each equation has n terms, and it has m equations. Okay, so once again, I've gone to the extreme and I've given you sort of a definition of what it means to be a system of linear equations by giving you like almost the biggest possible example, right? But let's take a look at a smaller example. Okay, so here's a system of equations in two variables, two equations in two variables. And just before we take a look at the next piece here, I want to just reiterate what I said in the previous this bit up here, which is to say that the two, let me use some color here. the 2 in front of x sub 1 in the first equation is my A11 because it's my first equation, my first term. The 3 in the first equation is my first equation, second term, so that's my A sub 1, 2. Occasionally, rarely, but occasionally you'll see these annotated as A sub 1 comma 2, and that's to distinguish the 1 and the 2, the subscript 1, 2 from 12. It's not subscript 12, it's subscript column 1, row 2, or sorry, row 1, column 2, or first equation, second term, as opposed to the 12th of something, right? So I just wanted to reiterate that and give you that little nuance that sometimes you'll see. Context really is everything here. So if I'm looking at the system of equations we have up here in my previous example, right, the work we were doing up here, I'm going to know that this is not A sub 23. That is not A sub 23. It's A sub 23 because of the context that I'm in. Okay, so here is a system of equations in 2 variables. Let's just annotate the last of those coefficients here. We've got a 1 in front of the x sub 1 in the second equation and a 2 in front of the x sub 2 in the second equation. So I have a 1 and a 2, a little bit of color coding here. This is my A sub 2, 1, because it's in my second equation, first term. Of course, there's a kind of an invisible one there. And the second 2, the yellow 2, is my A sub 2, 2. All right, this stuff is pretty pedestrian, pretty tedious, and pretty self-explanatory, but this annotation is very common and can get a little bit confusing here. Remember, this is not A sub 22. It has an equivalent, A sub 2, comma 2, second row, second column, or second equation, second term. All right, so now what we need to talk about is what it means to be a solution to a system of equations. To be the solution to an equation, you just have to be a number that makes the equation true. So, for example, 2x1 plus 3x2 equals 7. You'll notice that's the same as my first equation up here, the first equation in my system. But I'm not really interested in the system at the moment. I want to take a look at what it means to be the solution, first of all, just to an equation. And in this case, because I have 2 different variables, remember that I could have written this as 2x plus 3y equals 7. Right? There are multiple potential solutions to this equation because there are 2 variables, but there's only one equation. For example, I might have y equal to 2, and that x equals a half. That's going to give me 1 plus 6 equals 7. Okay, so there's one solution to that equation. But here's another one. When x equals 2 and y equals 1, we also get 4. 4 plus 3 is 7. So we also get 7 there. So we have the solution 1, 2 for x and 2 for y. And we have the solution 2 for x and 1 for y. And both of those work in this equation. But do they work in the system of equations? My other equation is x sub 1 plus 2x sub 2 equals 5. And if I change that one into an xy instead of an x1, x2, I get x plus 2y equals 5. And let's try our first solution here. If x is a half and y is 2, I get 2 times 2, that's 4.5 or 9 halves. That is not 5. So this is not this pair of numbers here, 1/2 and 2, 1/2 for x and 2 for y. This works in one equation, but not the other. So let's try 2, 1. if x is 2 and y is 1, I get 2 times 1. That's 2 plus 2 is 4. That is also not equal to 5. So neither one of these solutions to the first equation is a solution to the second equation. Let's see if we can find a pair of numbers that is a solution to both equations. I'm running out of room here, so I'm going to put a box down here in the corner where I'm going to test one more pair of numbers. I have 2x plus 3y equals 7 and x plus 2y equals 5. And I'm going to test the pair of numbers -1, 3, x equals -1, y equals 3, or x1 equals -1, x2 equals 3. So let's put a -1 in for x in both equations and a 3 in for y in both equations. And then we'll do the arithmetic. I'll do this first equation down here. 2 times -1 is -2, plus 3 times 3 is 9, and that does in fact equal 7. And for the other equation, -1 plus 2 times 3 is 6, and that does in fact equal 5. So -1, 3, if I add that to my list of potential solutions down here, -1, 3 is in fact a solution not only to each individual equation, but to the system of equations. 1/2, 2 and 2, 1 were solutions to the first equation in the system, but they were not solutions to the second equation, and therefore they were not solutions to the system. The only one on this screen anyway that is a solution to the entire system is -1, 3. And as it happens, that is the only solution to this system. You can check to see whether a particular pair of points is a solution to a system of equations simply by plugging the values for x1 and x2, or x and y, into the system, into both equations in the system, in the way that I did in this box at the bottom right-hand corner of the screen down here. And that's how you check to see whether a potential solution to a system is in fact a solution.